Great. So it's a great pleasure to welcome our next speaker, Claudia Scheimbauer from Munich, who will be speaking on extending topological field theories.
So thank you very much. Thank you very much for organizing this program. You look at the speaker list and it's very impressive, and it's a pleasure to be part of this. So what I will be talking about today is about subjects related to extending topological field theories. The title is rather broad and vague on purpose. I'm not quite aware what the background of all of you is, so I will try to start very gently and then get to some results, and hopefully you've seen some things towards this direction in the last 2 weeks. So roughly the overview will be that I will do some either recollection, or maybe this is the first time that you're seeing this type of approach to topological field theories, describing them as certain functors. So using the mathematical language of a symmetric modular functor. And we will see that trying to incorporate something like locality leads to wanting the mathematical structure to not just be a category, but a higher category. And I'll try to sketch what that means without going into details. So we will talk about, an ingredient of this functor, namely what the target of this functor should be in the next step. And then we will talk about a specific family of such targets. They're called the Morita categories, and try to use the famous cobordism hypothesis to understand what topological field theories appear. So why do we care about these Morita categories? Well, they are relevant targets for studying theories we know and like, such as Turaev-Biro theory, but also they're related to Reshetik-Turaev theory, which is somehow a mathematician's incarnation of Chern-Simons theory, if you wish, an approach in that direction. We will talk, I will give an outlook on work in progress, which is very much work in progress, on how to use that target and an enlarged version thereof to get these Reshetik-Turaev theories. So please feel free to interrupt at any point if you would like more background or details. This is the rough plan, but as I said, I'm not entirely sure what the background of the participants is. So if you would like more details, feel free to interrupt. All right, so let's start. Okay, so this was our plan. So let's start with our first point, the functorial approach to topological field theory. So these ideas go back to some people I mentioned here above. So Atiyah and Siegel certainly were the first ones to have this idea of this functorial approach, which I outlined here. So an n-dimensional topological field theory, this mathematician's approach, is to have an assignment, by which I mean a functor, so that if we have a closed n-1 dimensional manifold, then this is assigned a vector space over C. So you should think of this here as being your space, like the space we live in. I mean, maybe more naturally to think of this as R3 or a three-dimensional manifold, and then the target will be the state space that we attach to the quantum field theory. And then I also want to understand n-dimensional cobordisms. So what's a cobordism? It's just a manifold with boundary now. So you should think of this as space-time. So this is my time direction. And here I have my space, maybe three-dimensional and three-dimensional space. And then I have four-dimensional space-time. So that's where the +1 comes from. So a cobordism is just a manifold with boundary, where the boundary has a disjoint union. Part of it is an incoming and part of it is an outgoing. And to an n-dimensional cobordism, we assign a linear map. And this you should think of as the evolution or evolution operator. And this assignment should have, should be more. I said it should be a functor. So what does functor mean? It means that my morphisms in my category. So these will be the objects and these will be the morphisms in my category. And how do I compose such guys? Well, I glue them next to each other. So for instance, if I take the cobordism that I just drew, and I might have another cobordism, something like this. And now you can see that, well, this outgoing part is the same as the incoming part here, so I can glue them. Just take this and glue it. And by this, I obtain a new cobordism, now going from these two incoming parts to the outgoing part. So composition, gluing of cobordisms. So to make this precise, we need to be a little bit more careful. We usually want our manifolds to be smooth, so we should take something like diffeomorphism classes of, maybe my color coding is off here. So we should actually take diffeomorphism classes of these things, but that really means something to you if you've seen it before. If you haven't, just take it with a grain of salt. And the other property that we want is, so it should be a functor. The other property it should have is it should be symmetric monoidal. So I can take disjoint union, so both of my one-dimensional manifolds or of my cobordisms, I can take a disjoint union. And on the other side, it should be sent to tensor product of vector spaces and tensor product of linear maps. So this should encode, in some sense, that if something in the field theory happens far away from each other, then, well, the state spaces just are given by tensor product. Okay, so maybe an immediate consequence I would like to note here is that I can view a closed n-dimensional manifold sigma. I can view as a cobordism from empty to empty. So my empty sets will be an n-dimensional manifold for any n, or in this case, n-1 dimensional manifold. And so being symmetric monoidal will imply that if I call my field theory Z, that my Z of sigma will be a linear map from Z of empty set to Z of empty set. But Z of empty set, by saying it's a symmetric monoidal functor, this should just be my ground field. So in this case, I said my ground field is just C. So I get a linear map from C to C, which corresponds to just, well, it's fully determined by the value at 1. And this is a number in C. And this will be a diffeomorphism invariant. So this is how TFTs in this framework are related to getting invariance of manifolds. Are there any questions so far? Yeah, thank you very much for posting the link. This is a link to, if you look at the chat, there's a link to the automatic backup of these notes. So if later in the point in the talk you would like to go back, feel free to go there. All right, so let's scroll down. So let's now take this definition. Our next step will be to go and modify this definition a little bit. So as a mathematician, it might be a little bit arbitrary that we singled out these two dimensions, n and n-1. Okay, so here I just repeated the slide here. It's again just n and n-1. And that might look like a bit of a funny choice to you as a mathematician. And also as a physicist, especially in some of the talks in the last weeks, you might have seen that maybe a field theory might not just assign something to space or space-time, but also higher codimensional manifolds, or maybe some corners, or maybe some branes, sometimes they're called, and so on. So now, and this is where these last two people come in, we will try to modify this definition and not just restrict to these two pieces. So I will erase this part here. That will reappear. I will also erase this part. And now we will what's called extend this. So now we also will replace my closed n-1 dimensional manifolds by now n-1 dimensional cobordisms, and add n-2 dimensional things. So a priori, I should now write closed, but I don't want to stop there. Why stop? I could go on, n-3 dimensional. And then I have to put cobordisms here. And so ultimately, if I continue this, I will end up with points, which are the closed, but zero-dimensional manifolds. So one might hope that my field theory actually assigns something to all of these things. So maybe let me write here one-dimensional cobordisms, and I'll draw a picture. And then my two-dimensional cobordisms. So I have my points, and then in 1D, I have maybe something like this. In 2D, I have the pictures that I had before. But I also allow something funnier. So I might have something like this. So corners start appearing, right? This is the important part, that now we have corners that start appearing. Okay, great. So before, it was just very useful to summarize this assignment here into saying it's a functor and it's symmetric monoidal. So functor means it's a functor. Maybe I should have added this here. A symmetric monoidal functor of categories. That was because we explained how these are the objects in a category and these are the morphisms in a category, and we saw composition down here. But now in this gadget, now I have a lot more layers than just objects and morphisms, and the structure here is most naturally described as what's called an n category, or actually an infinity n category. And well, you have to actually build such a thing, and that's something I did with Demia Kalak a while ago, following strategy by Lurie. So now we know what to put on this side. And now I can say my definition, extended, or sometimes this goes under fully extended, n-dimensional topological field theory is a symmetric monoidal functor of infinity n categories. So the key message here is that, well, these infinity n categories just show up naturally. It's just the structure that just happens to be on this side. Okay. That's just the thing that we have there. But now the question is, what do we put on this side? Okay, we will want to have a generalization of our old definition. So here, right, and I should call this something. This is called board n going to 0. And this right-hand thing I will call C. And here we want to have something like something like vect, to be able to recover the old notion. But we will want more. We want to understand what to assign to these lower parts as well. All right, so a natural question that might now appear is, in topological field theories, usually we start with the partition function. We have something we want to assign to n manifolds, or maybe even we already have an n-dimensional topological field theory, like in our old definition. And then the question is, can we actually extend our old structure to get a functor of this sort now instead? So we will recover the old thing here at the top in these top two layers, but can we arrange that so that we can extend? Okay, are there any questions so far? Okay, so the next question will be that I would like to address is what to put on this right-hand side. And why this might be a useful notion. Maybe let's answer that notion first before answering answering what to put on the right-hand side. So why would we want to actually produce this beast? Why weren't we happy with the definition that we had just at the top here? And one of the answers is, well, I mean, one of the answers you might say is, well, physicists have shown how to assign things to codimension 2, codimension 3, and so on, manifolds. And we would like to understand how that's functorial. So that's certainly one answer. And why would we want to go all the way down to points is the other question. And the answer is given by this beautiful theorem, this beautiful cobordism hypothesis that I wrote here at the bottom, which says that extended TFTs in this sense, so I should add the word fully here, they are local. So this really expresses locality. And what the theorem tells us is that if we take such extended n TFTs valued in some C, and this should have some extra structure called a framing, then I can fully classify them, and they're fully determined by what happens at a point. And the value of this point is what I called n-dualizable here. That's a property that we will talk about in the rest of the talk. So that's the point somehow here of this beautiful result, that it really expresses physical locality. And conversely, this allows us to produce many nice TFTs. Namely, I start here, I find my favorite C, I check whether an object is dualizable, and then the cobordism hypothesis tells me I have a TFT. Computing this TFT is a bit of a problem. Then you have to start working quite a bit, but at least you have an existence. All right, so what types of things can C be? So my target C can be various things. We already said the desired property is that we recover vect, or maybe you want super vector spaces, or some other linear favorite thing for example, chain complexes or modules or something like this at the top two levels. So in mathematical terms, how I can describe this, I can say, well, in my symmetric monoidal category C, I have the identity n-2 morphism. So now I'm lying here. I take the identity, which is in here. So I didn't tell you what an n category is, but I mean, you also have identities just as in any category. And now what I can do is I can just take endomorphisms of this thing. And this should be my vector spaces or super vector spaces that we started with. Another way of writing this, and for topologists, this makes a lot of sense, but we write this as the n-1 fold loop space. So this is a desired property, and the consequences given a fully extended TFT then I can actually do this looping procedure to my Bordism category. And what I obtain is just the one that we had before, just the board n-1. I think I didn't give this a name, but that was just the classical one that we had on the first slide. And on the other side, I land in omega n-1c, which is just vect. So I recover unusual TFT at the top. That's why. So this is really a generalization. All right, so let's look at some examples that I can put here. Let's look at some examples of C. And so an example, let's start with n equals 2. So I want a 2 category. So this will be called alg, or I will call it alg1 of vect, and you will see later why. So this should be a 2 category. And again, I'm brushing over details of what a 2 category is. Feel free to ask me later. But what it should really be, for the purpose of this talk, it's enough to know that it has some objects. It has morphisms, which I will call 1 morphisms. And it has morphisms between morphisms. So it has 2 morphisms. So what are my objects? Well, suggestive name, they're algebras. What are 1 morphisms? So I have to tell you if I have 2 algebras. And I have to tell you what hom from A to B is. And this will be a category, namely, they're AB bimodules. And then my morphisms in this category, which are the 2 morphisms, are bimodule homomorphisms. Okay. And so note, I forgot my color coding. So note that if I just take, let's say this is vector spaces over C again, if I just take CC bimodules, it's the same thing as just a vector space. And then homomorphisms, those are just linear maps. So indeed, here I have that if I just loop my alg, this will be equivalent just to vector spaces. So indeed, it has the property that we wanted. Maybe I should have told you what's composition. Composition if I have an AB bimodule and a BC bimodule, then this will be the relative tensor product as an AC bimodule. Okay, there's a question. Should we think of the objects associated to a point as being some analog of an algebra of local operators? That's exactly the point. Thank you very much for that question. That's so on point. So especially in this situation right now, you really see the algebras appearing. This is really, you should really think of that as being the algebra of local operators. So we will actually push that further in the next steps. So that's exactly on point. Yes. So sometimes, so in this situation, it's really, if we have the algebra as a target, it's really that. They can have a bit of different flavors. A different choice of target here could be to take k-linear categories and functors and natural transformations. And then you can think of these categories as, say, the category of boundary conditions, something like this. Does that help? Great. Okay, so let's look at, let's do one more example. So you might have heard of Turaya-Vira theory. So this is 3, 2, 1, 0 extended. So that means I can assign something to 3-dimensional, 2, 1, and 0-dimensional manifolds. And this takes values in, I will call it Fuge for fusion categories. And you will understand where this comes from later. It's in Alg1 of cat. See? So notice the analogy to before. There we had Alg1 of something else. Now we have also Alg1 of something. And so now here I will again just write down objects. These will be the fusion categories. Or in this bigger one, they will be tensor categories. Morphisms between morphisms will be bimodule categories. Two morphisms will be linear functors. And 3 morphisms, natural transformations. So I'm just writing this down. Of course, it takes some work to actually construct these things. I haven't told you what these categories are at all. And we will get to that in a moment. So fact is now that if you take the 2 looping of this thing, you also get vect, or maybe the finite dimensional part, but for the purpose of TFT, that's fine. Okay, and the fact that the proof of this result, the first one was by Douglas Schoma-Priest Snyder, and in a slightly bigger context, there's a reproof of part of that result by Brochet, Jordan Snyder. So using this strategy here. So we have this category, and I will tell you a little bit on how to construct that category. And then what these people did was they took that category, 3 category now, and proved that fusion categories indeed give n-dualizable objects. And then there's some work to do for orientation. Are there any questions at this point? Maybe let me put this here. Okay, so what are these Alg1 of blank? Okay, so this was something that both of our examples happen to be this, and the answer is a higher Morita category. So I will now tell you about a generalization. Namely, it's just alg now n, and I can input something more general called s. So this here is some integer, and this here is some nice category. And this can even be a higher category. It can be an infinity k category. So for instance, we had vect, which was just a one category, just a category or a one category. But we also already saw cat c, which is a two category. And so this here is just n greater or equal to 0. So we saw two examples of this. And so here I would like to attach some names. So there are two constructions of these things as higher categories. One of them is due to myself and Daniel Kalak, and another one by Rune Haukseng using very different methods. And then both of these constructions were actually extended by Theo Johnson Fried and myself. So you need all three of these papers. And so let me very informally list again what are my objects and morphisms and so on, and then I'll tell you a little bit about how to think of these things. So objects are, coming back to your question, exactly local observables of an n-TFT for n dimensions. Another description of this in mathematical words is these are EN algebras. Or another description, which might have showed up at some point in one of the talks, is it's a locally constant factorization algebra. So I should say here, maybe I should write equivalences here, because I mean, this is actually a non-trivial thing one has to prove, and was proven by Jacob Lurie. And this is actually hard. But the picture you should have in mind is exactly that these are the local observables of your n-dimensional topological field theory. And these have a certain structure. So, I mean, yes, they're algebras, but they're even more than algebras. So for n equals 1, an E1 algebra is just an algebra. And for higher n, if we just have vector spaces, we will get a commutative algebra immediately. If we have categories, then we will be in this situation, and we will have E1 algebras and categories are just tensor categories. If I go to n equals 2, E2 algebras and categories are actually braided tensor categories. Okay, so wrong color. So for instance, a modular tensor category. Which, yay, are exactly the things that we need to construct, say, Witten-Rishchik and Turayev theories. So that's why you might be interested in these things. Okay, so let me write down the main theorem. Yeah, maybe, so the first part is by Owen, William, and myself. I need a little more space. Which says that now, remember, how can we attempt building fully extended TFTs? We want to go back and use this theorem here, this result. So it told me that if I want a TFT, I can instead just look at my target and check for n-dualizable objects. And that will be the value at the point. So this will be the value at the point of my TFT. So now I have my chosen target. Now I can ask, what are the n-dualizable objects? And so this is what Owen and I answered. In Alg n of S, every object is n-dualizable. Hence, using framed TFT. The second part, which actually was an older result of mine in that same work as was written above, is that actually we even know how this theory works in general. So this is actually given by what's called factorization homology. Okay. Right. So you might think, whoa, great, we know what the n-dualizable objects are. The problem is that this here is not just an n category, but actually it's much larger. So this here is an infinity n plus k category. So this is the k, and this is my n. And if you look at my examples, here I wanted a 3D TFT, but I was working in Alg 1. So I'm not really interested in one dualizable, which gives me a 1 TFT. I'm actually interested in 3 dualizable to get a 3D TFT. And so this theorem only tells us something about the lower levels. It doesn't tell us about the upper levels, and this is where conditions will appear. Okay, so how do we go about defining such a category? To say, yeah, maybe before I explain, give an outline of how you might go about attacking this problem and how to define these categories. Maybe I would like to comment on how to get from what does locally constant mean is a question. Okay, so the question here is, what does locally constant mean? And a bit later, I would like to give a couple of comments before, but a bit later, I will tell you what a factorization algebra is and what locally constant means. So roughly, you can think of a factorization algebra as assigning something to disjoint unions of disks. And locally constant means that if I have an inclusion of disks, then the value that's assigned will be the same. So it's the same as a locally constant sheaf, for instance. It's the same type of condition, but we'll get there. So first, I would like to pick up that we were talking here about modular tensor categories being some examples that fit into these guys. And so a question you might have is, are these targets AlgN optimal? So I mean, are they all to describe any TFT that I want? And I mean, the answer, this is a very vague question, of course, because it depends on a lot of things. But the answer I would like to convince you is no. And so an example I would like to pick up is the Witten-Reshetikhin-Turaev theory. So what's the Witten-Reshetikhin-Turaev theory? So it's known that if we're given a modular tensor category, and so maybe you would like to keep in mind the example of representations of UQSL2 of the quantum group. And then, well, to get a modular tensor category, you have to take like Q, a root of unity or something like this. And so given such a modular tensor category, we get a 3-2-1 TFT. And this will be valued in our linear categories. So this is known. And it extends the original construction, or it's a reformulation of the original construction by Reshetikhin and Turaev. And now we can ask the question that we've been asking before: can we extend down to points? So you see that we have here 3-2-1, but 0 is missing. So we can ask, well, can we extend down to points? And one first answer is, well, one first question you might want to ask: can we extend to port 3-2-1-0? And now the target that we've been talking about all the time is this Alg1 of cat. And the answer is actually no, not in general. So if my modular tensor category is what's called the Drinfeld center of a fusion category, then yes. So that was a result that I mentioned above here. But in general, no. So, but maybe I should break this in red because this is an objection problem. Not every MTC arises this way. And so maybe I should add here is that these give a theory, the Turaev-Viro theory. And so now here we have that if I take the Turaev-Viro theory attached to A, then this is the same thing as this Reshetikhin-Turaev theory attached to the center. But not every MTC arises this way. This has been known for a long time. I think it's due to Muger. So certainly this target here is not good enough, and we want to extend this. So we want a better target. Another remark I would like to make is that for invertible fully extended TFTs, Fried and Hopkins tell us there is an optimal target. which is called sigma n IC star. And well, this is universal in a certain sense. So the theory will be fully determined by its partition function. And so a question that I would like to know the answer to is, can we find a similar one? So Theo Johnson-Fried and Davide Gaiotto have an approach to this question, but we still need to understand a lot about this. So there's a question: is the then yes line a conjecture or a theorem? Then yes, that's a theorem. That's a theorem. I would have to think who proved this. I can tell you after the talk. I can think about that. What is an example of an MTC that does not arise as a Grunfeld center? Ooh, I'm not an expert on these things. I apologize, but that's something I cannot tell you. I can point to you where to look for it, but I can't tell you. Well, actually, maybe I can, because this one here, because this is the one that we want to have. This is the modular tensor category that arises here as the value of the circle. But since we can't extend it down, this certainly is not value a Grunfeld center. Okay. Great. So, so back to the Witten, Reshetik, and Turayev, we saw that alg 1 of cat or fuse is just not good. But the question is, can we do something else? And so outlook. So an MTC C is an object, and now if I take alg 2 of cat instead of alg 1 of cat. So this was the first example that I gave you here. Look here. This was our first example. So it's an E2 algebra, so it's an alg 2. And some authors, Rocher, Jordan, and then one of the papers is together with Pavel Safronov. Sorry, apologize, spelling mistake, Safronov. And the other one is without. They show that C is four-dualizable, even invertible. So this gives an invertible TFT. It's not the fully extended TFT, but it's not the one that we want. This is the anomaly of the theory. It's an invertible one, so it gives an anomaly. And something that now we should get, and well, details are maybe technical details here are to be filled in, but more generally, C, have I been calling this C? Yes. C gives a theory relative to this anomaly. So I'm not telling you what anomaly means or what for a mathematician or for me means, but this anomaly theories or being relative to an anomaly means that I don't really have a functor like I had in my definition. So relative means that we have to modify our definition field theory. And there are various approaches to doing this. So, I mean, this definition goes, this notion goes back to, was introduced by Fried and Tillemann. And then there is also a related notion suggested by Stolz and Teichner called twisted field theory. And then maybe we want to be able to talk about that and have a mathematical language for it. And classification. And so one of them is due to Theo Johnson-Fried and myself. And another one using boundary field theories is at least a conjecture by Jacob Lurie. So there are some frameworks here that one can use. And to show cobordism hypothesis style, that C indeed gives one of these relative field theories. So there are still a few details. But... Okay. Great. So we have a relative field theory. But now what is work in progress with Fried and Tillemann is to enlarge this category Alg1 of cats, or actually this fuge inside, by adjoining, I will call them roots, or pre-centers of a modular tensor category. So we get something, maybe I would like to, for the purposes of this talk, call fuge of x comma y. So maybe x comma x dual. And this relative field theory gives a symmetric monoidal structure. And then X is, so this is a 3 category, and this is actually 3 dualizable. It gives a 3D TFT, which should be rich and rich to derive. So there's a question in the chat that asks, is the statement that any E2 algebra in C linear categories gives rise to an extended relative field theory in what dimension, or MTC? Yes, so any MTC is an E2 algebra in cat C. And the statement would be that you can view the MTC as a module for itself, and that gives a relative field theory. So in which dimension, I would have to go into details of these different frameworks. So maybe we can talk about that after the talk. All right, so this is an outlook on the work in progress, but I promised to you previously that I would tell you a little bit about these categories, these Morita categories, and how you might go about proving dualizability. And so for now, for drawing pictures, I will just draw the pictures for n equals 2. Also because then you just see the structures appearing a lot better. And so the main tool here are factorization algebras, but not just any factorization algebras, but constructible ones. So for instance, constructible could be locally constant. That's a particular case. So what are factorization algebras? So factorization algebras are co-sheaves, but not normal co-sheaves, but co-sheaves for a funny topology, for something called the Weiss topology. So in particular, oh yeah, and all of our factorization algebras will just be on R2. So generally Rn, but now we're in the case n equals 2. So in particular, my factorization algebras assign something for a disjoint union of U1 to UN sitting in some V, sitting inside R2. We get a map from f of U1 tensor f of UN into f of V. So this is what you should think of as the multiplication of the observables. So remember one of the examples here that was also asked for were locally constant factorization algebras or local observables of an n-dimensional topological field theory. I should say perturbative here. Maybe that word was missing. And you should think of this here as the multiplication of observables. Product of observables. And so I would just like to finish by drawing a few pictures. So we had as above, we have objects, one morphisms, two morphisms, and my objects will just be constructible, so locally constant. Constructible. Factorization algebras on just R2 with no stratification. One morphisms, I just repeat the same here, and I will need it once more. So repeat. And now here my base space is again an R2, but now I add a stratification, which is a vertical line. So this is in here, I have some S cross R. And my two morphisms now will be constructible factorization algebras on the same type of picture, but now I have a little flag. So now I have R2 in there, my S cross R, and in there a point S comma T. Okay. And how to think about what's happening here in E2 algebra? Well, we're allowed to draw inclusions of disks like this. So I would just like to finish by showing you a picture or two. So I redrew here on the side, I redrew my space on the left here. So what this has in particular is I have an E2 algebra that's sitting here. I have another E2 algebra that's sitting here. And on this line, I actually have an E1 algebra, because if you forget the blue and the red, I'm just left with a black line, an R1. And on R1, by the previous step for n equals 1, I have an E1 algebra. And so you include now these two disks into this wobbly one, the wobbly one looks the same as the disk on the black line, so it's the same thing. And this tells me that this E1 algebra on the line is actually a module for this E2 algebra. Okay. And similar arguments work here. You get bimodules of bimodules. And the dualizability things that we have to prove, in essence, it boils down to string diagram arguments. So I just finish with showing you the picture, showing an adjunction where, I should erase these lines, where you can see my little morphism, my one morphism is sitting here. And indeed, this piece here is the co-unit for the junction, and this piece here, oops, sorry, this one here determines a unit for the adjunction. And I don't want you to take more out of this than just to seeing that there are string diagram type arguments that start appearing. So in some sense, one can translate what we do into a sort of a calculus, string diagram calculus, for dealing with these E2 algebras and bimodules. Hopefully that's a takeaway message for you. All right, so thank you very much. Thanks for paying attention, and feel free to ask any more questions.
Thank you, Claudia. Fascinating talk. Questions? Aswin, you had a question.
I think she answered my question during the course of the talk, but I think Pranav had a question.
Okay.
Somebody
Pranav.
has raised their hand. Is that
Yes,
Pranav?
Pranav.
Yeah, it's me. Hi.
Hi, nice to see you.
Nice to see you. Thanks for the nice talk. I have many questions, so maybe I'll ask one or two, and then I don't want to hold up.
Yeah, sure.
So maybe let me start with the slide you're on. So these pictures you're drawing, I mean, the things you've described so far in these pictures still looks like stuff you would see in the E and Morita category, right? So are you just describing that, or are you describing some enlargement here?
No, this is really the E and Morita category right now.
Okay, you're just describing the
Yes, this is just the E and Morita category, absolutely. I should have given the name again.
No, I was wondering if this is part of describing this enlargement that you're
No, the enlargement is actually very formal. So this is really we're just basically adjoining an extra dualizable object in some sense, in a very formal way. As an n category, as a 3 category, this is not very difficult. It's just taken by adjoining, it's just a coproduct. But the tricky part really is to find the symmetric monodal structure.
I see. Great, thanks. And so if I can go back to the other question I asked you. So I know that MTCs are E2 algebras, but they're not just E2 algebras in categories, right? They're E2 algebras with extra structure.
Yes.
So now you had a statement that any such, I didn't quite understand what the statement was. If you can go back to the result of those 4 people, yeah.
Yes, so what they show is that in this category, the MTC is a particular object in there, right? It's an E2 algebra. It's more than that, but in particular, it's an E2 algebra. So by Owen and my theorem, it's already 2 dualizable. But what they show is that it's not just 2 dualizable, it's even invertible. So by the cobordism hypothesis, you get a 40 TFT valued in this thing, which is invertible. So, well, it's framed. Dealing with orientations is something that's still a question how to do, but it's framed. And this invertible theory is supposed to be the anomaly of the theory. I think it's called Pranav theory. And now, I didn't tell you how this classification works, but the classification works via taking not just an object in here, but a morphism in here. And so the morphism I look at is C as a module for itself. That's a morphism in this thing here. And now I mean, there are points here on purpose, right? Because there are some technical things that have to be worked out, but this should give a theory relative to this thing. So, I mean, the other thing I have to be honest about is that, well, again, orientations are a problem. So, I mean, as a framed theory, that's something we can get. As an oriented theory, that's something where you actually have to still work quite a lot.
Right. And
I don't know how to do that.
Right. So that's about understanding homotopy fixed points. Yeah. Some SO4 action.
Exactly.
Well, SO3, I guess.
So as far as I know, these authors have been working on this, but I don't know what the status is. Due to the pandemic, it's harder to meet regularly. Yeah.
So yeah, I guess, I mean, four dualizability is a really hard thing. So I mean, do you have some comments on how, I mean, being four dualizable?
I just didn't hear what you just said.
Being four dualizable is a really hard condition to check, right? So do you have some comments on what, what the idea is? Like, why is it even possible to check this?
Well, I mean, for up to dimension 2, we have a very concrete, constructions of the units and co-units that are involved. Mm-hmm. And then you're in a setting where you're essentially working in Cat-C. Mm-hmm. So you can first ask the same question in Cat-C, and then try to, how should I say, lift the dualizability data that you get in Cat-C to include somehow the module data. So I can mention actually that Lurie already had a conjecture in general in Alg n of S, how to get n+1 dualizable objects. So what these authors proved is a version for n = 2 and the specific case of Cat-C with the properties on Cat-C that I haven't been telling you about to hide some technicality. And so the conjecture by Lurie gives you 3 dualizability. And so what they actually show is that to get invertible, you need 3 dualizable plus 1 extra, maybe it was 2 extra conditions. And so maybe this is a little advertisement. So for n = 2 and any category here, my PhD student is working on, has an argument on how to prove this conjecture. She hasn't written it up yet, so that will take a little bit of time. But
and just to confirm, when you say Cat-C, did you mean DG categories or some such thing, or did you mean just K-linear? I mean, just usual.
No, really K-linear categories. So they work in 2 different settings. So this first paper without Pavel, they work in presentable K-linear categories or locally presentable K-linear categories. In the invertibility paper, I think they work in the same context. They have a slight variation, but minor differences. And this is also the difference. So I mentioned here before earlier these results. So these authors worked for finite tensor categories, whereas here they go to the locally presentable case. As far as I know, in the GG setting, I'm not aware of any things that have been worked out.
Thanks a lot.
Thank you. Aswin, did you have a new question, or is
yes? I do have a question. So the example where you were talking about the conditions under which a modular tensor category is fully invertible. Mm-hmm. So if I understood right, so that's the setting for Chern-Simons theory, right? I think the example you had in mind was pressure-taken to arrive.
Exactly.
So the condition that it should arise as the Drinfeld center, what would that mean in, like, say, physics language? Is it possible to translate that?
Ooh. That's a great question, and I have absolutely no idea. But it's certainly something I will try to think about.
So I only sort of know like the abstract definition of a categorical center, but in some examples I know it's related to, like, if you can get something as a dimensional reduction on a circle or something like that. I don't know if that is true in this case. I don't know if that's true in this case.
Well, so maybe to mention some words relating to this. So what's happening here is that such a functor is determined by the value at a circle.
Mm-hmm.
So that's what the modular tensor category will be. And so if we start with a theory like this, then we can actually evaluate this theory always on something cross circle. And that's related to dimensional reduction along a circle. That's what, I mean, the mathematician's language for reduction along the circle. Right. And so naturally, if we take a theory like this and do dimensional reduction along a circle, we will get automatically a Drinfeld center. So these are the Witten-Reshetikhin derived. I mean, if you want in these words, the Witten-Reshetikhin derived theories that come from the Drinfeld center are exactly those that come from the dimensional reduction along a circle of a Turaya-Firo theory.
I see. Okay. So I think that should be something that physicists should be able to make sense of. Maybe somebody already has, but I don't know. Probably
they have, but that's where my lack in background in physics comes in, I admit.
Okay.
Yes.
But that was helpful. Thanks.
Okay. Great. Sorry, Pranav, is that a new hand or an old hand?
Yeah, it is.
New hand, okay, sure.
I have one more question. So I want to ask about this example, Claudia. You said, so it's a follow-up to Aswin's question. You said that I think this quantum SL2 is an example where it's not a Drinfeld center?
I think that's correct, because I mean this is the one that we're interested in for the classical, Witten's description of Chern-Simons theory, right? So that's the case that we want for Q a root of unity. But well, I mean, for a modular tensor category, it's just not known how to extend time to points, right? So by circular reasoning, I can tell you that it's not a Drinfeld center, because otherwise we would know how to go down to a point.
Right.
But that's of course a bad answer. I mean, because I'm using hard technology here. I'm sure there's a more direct answer to how to see that this is not a Drinfeld center. I mean, there is, Muger has these. There are these obstructions and obstruction groups and so on that you can compute. And you have to see whether, what the class of this thing is in there. But I don't know how to do these computations.
Right. Though, so it's not clear to me why. So suppose I know that some category is a Drinfeld center of something else. Why is it obvious that the field theory determined by, so in your thing, it's M is the center of A. So why is the field theory determined by A the same thing as,
so it's not obvious. It's not at all obvious. Depending on your description, it is or is not obvious. But so the thing I can maybe add here is that note, if I take any theory and I evaluate it at a circle, what do I want? Right, so I want my A theory evaluated at a circle. And so for the circle, for the S1, I take with an interesting framing. I wanted to draw a picture, but it's becoming a bit small. So the framing I want here is maybe I will add an extra page. It's becoming a little bit too small. So so I can take my S1 with interesting framing. So I take the blackboard framing, the one that's bounding. And then if I take my ZA of S1, this will be computed as the Drinfeld center of A. So this is think if we have A in algebra, then the A of S1 for algebras is the Hochschild cohomology.
Yeah, this is clear, but then why is it on all other manifolds you need to know that the theory is the same as?
Right, but in both cases, it has been proven. So for this, we have the cobordism hypothesis. And for this, there is a classification by Bartlett, Douglas, Shoma, Priest, and Vickery that this is fully determined by the value at a circle.
I see.
As a modular tensor object in here, where I didn't tell you what that means.
I see.
So it's enough to understand what happens on the circle.
Thanks.
Okay.
And so maybe here another remark, if this is underived, I just get the center of the algebra. So it really is again a center. All right, now I'm done.
Great, thanks. So if there are no further questions, let's thank Claudia again for a really fascinating talk.
Thank you very much for the invitation.
Thank you.